Hey everyone. Today on our Chapter 9 practice test, we're going to be looking at these problems that have to do with the comparison test. And another comparison test is it makes people nervous because it's kind of unknown. It's up to you to figure out what functions you should be using for comparison. So just to recap, if you believe that a function, as you take the integral to infinity, if you believe that that function, like this function, if you think this function is going to converge, then you want to compare it to a function that's bigger that also converges. And if you think that that function in the integral, the definite integral, if you think that's going to diverge, then you want to compare it to a smaller function. And the trick here is really that you should have some kind of an idea about whether or not this function is going to converge or diverge before you even start your mathematics. So I'm looking at this function, and I have to consider what is the effective power of the denominator. Because if the effective power of the denominator is greater than 1, if that effective power on the denominator is greater than 1, then the integral is likely going to converge. And that if the effective power of the denominator is less than or equal to 1, we're probably going to see something that diverges. So we have to consider and balance the behavior of the numerator and the denominator to figure out that effective power. So looking at this very first problem, 2 plus cosine x on the numerator, I know that cosine x is a function and it takes on multiple values, but when you come right down to it, the cosine value of x always lives between -1 and 1. So we're always assured that the function is always greater than 2 plus -1 over x squared, and it's also always less than 2 plus 1 over x squared. So in essence, when x gets really big, let's say even when x equals 100, 2 plus 1 and 2 minus 1 aren't really that far apart anymore. 3 over 100 squared is pretty much the same thing as 1 over 100 squared. So that numerator, I don't consider that having any power at all. So the only thing here is our denominator, and our denominator has an effective power of 2, so our integral is likely going to converge. Now what we've done here is also really nice because we have also figured out a function that is greater than our original function. So we know that 2 plus cosine x over x squared is going to be less than or equal to 3 over x squared. Now I think that the function that I'm analyzing is going to converge, so I'm going to pick the bigger function here, 3 over x squared. And let's take the integral of 3 over x squared. Well, I have the upper limit is infinity, so I'll need to have a variable to replace that. And then now that I've replaced that upper limit, we can start looking at the antiderivative. Our antiderivative is -3 over x, and we're going to evaluate from pi to b. And after we do the substitution, you notice here that this limit, as b approaches infinity, this denominator here is going to grow without bound, while this numerator is going to stay constant. So we've talked about that before. If the denominator grows without bound and yet the numerator stays constant, then this function is going to go to 0. And since that integral of the larger function converges, then of course any function that is smaller than 3 over x squared is going to converge as well. So since 2 plus cosine x over x squared is smaller than 3 over x squared, it converges by comparison. Now don't forget to write down converges by comparison here, because you are asked to use the comparison test. And if you don't give an indication that you've used the comparison test, then really what have you done? So with that one out of the way, let's take a look at this next one. We've got the integral from 1 to infinity of natural log of x over x. And we've got to talk about the effective power here. And the power on the denominator here, well, that's just x. And then the numerator is also going to grow, but at a slower rate than x. But whatever rate it is, it doesn't really matter, because what happens is, since the denominator is growing at a rate of x and the numerator is also growing at a rate of natural log of x, that means that my denominator should be growing at a rate slower than x. So basically, the rate of the numerator is going to decrease the rate of the denominator. So we're going to be looking for a function that is smaller than natural log of x over x. And there's a couple of ways that you can make a function smaller than the one that you're given. One way is to make the denominator smaller, because when you make the denominator smaller, you're creating a larger number. Just think about that. 1/2 is bigger than 1/9, for example. So a smaller denominator means a bigger function, which means a bigger denominator would be a smaller function. So we could try to find a way to make this denominator bigger. So for example, sometimes I see students try natural log of x over 5x. And yeah, you've made the denominator bigger, so you have a smaller function, but you don't really have a function that's integratable. And that's a problem. So the other thing you could also do is to make the numerator smaller. So if I make the numerator smaller, I have made a function that is necessarily also smaller. So what's smaller than natural log of x? Well, sometimes I see students try natural log of x minus 1 over x. And sure, that is smaller than natural log of x. But again, you've now created a function which is not integratable. So we got to find a function that is integratable. And the easiest and the cleanest way to do this, I think, is just to use 1 over x. 1 is definitely smaller than natural log of x as we start looking at numbers that get close to infinity. So 1 over x is going to be a really nice function for us to use, because that is smaller than natural log of x over x, and it is an integratable function that is smaller than natural log of x over x. So let's try the integral of 1 over x. Okay, I still see a problem here with the upper limit. We've got an infinite upper limit, so we're going to use the knowledge that we have to deal with that. We'll create a limit as b approaches infinity of the upper limit b. Now the antiderivative of 1 over x we already know is natural log of x. And now with our antiderivative, we can also substitute. Okay, now that we've substituted, we can take a look and say, well, hey, what happens with the natural log function as b approaches infinity? And, well, the natural log function grows without bound. So this part that I've just highlighted, that's going to go to infinity. So infinity minus a natural log of 1, didn't really matter what the natural log of 1 was. Infinity is going to quickly overwhelm that, and we get something that does not converge, or something that diverges. So since this smaller function's integral is going to diverge, this larger function being natural log of x over x, going to diverge by comparison. Again, remember to write that by comparison. Okay, with that one done, let's take a look at number 20. And 20 is kind of tricky, to tell you the truth, because you see something in the numerator, e to the negative t, and it doesn't register with your brain that you're not really looking at something in the numerator. In fact, the function that you're really looking at is dt over e to the t root t. So now the numerator has no power at all, and all the power is on the denominator. Furthermore, you've got yourself an exponential function in the denominator, which is one of the fastest growing functions out there. So no matter what you're multiplying it by, you're going to get something which grows faster than, well, you're going to have something where the effective power of the denominator is definitely greater than 1. So this integral is likely to converge. So now I got to find a function that's bigger than e to the t, square root of t. And it also has to be bigger in a way that I'm able to integrate it. So remember, there are two ways of doing this. You could make the numerator bigger. So you can maybe replace that 1 with, I don't know, 10. But this has the effect of giving you a function which is still not very integratable. I think you could probably still integrate this with great difficulty, but you shouldn't have to work too hard to integrate here. So that might not be a great idea. Now the other thing you could do is to make the denominator smaller, because if you make the denominator smaller, of course that function is going to grow in size, because 1/2 is bigger than 1/10, for example. So what could we do here to make this denominator smaller? Well, one thing that you could do is you can make one of these two functions, either the root t or the e to the t, you can make one of them just equal to 1. Okay, so which one is better to do? And if you think about square root of t just a little bit and the way that integral is going to work, the integral of 1 over square root of t is actually going to diverge. So that's a bad choice. And if you want to know why it's going to diverge, maybe you should take the integral of that just to see for yourself that it is going to diverge. So the best choice here is to compare it to 1 over e to the t. 1 over e to the t is integratable, and it is going to converge. So, we can already see into the future that that's going to converge. Hopefully you can by now. So let's take the integral of 1 over e to the t. And we'll do something about that upper limit right away. And also, while we're at it, 1 over e to the t is a little bit difficult to integrate. I think it's easier to look at e to the negative t power. Okay, that's a little bit better because I know the antiderivative to e to the negative t is negative e to the negative t. Now with my antiderivative, I'm just going to substitute. Actually, before I substitute, I'm going to change that e to the negative t back to 1 over e to the t. I think in this form, it's a little bit easier to see that you're going to get something that converges. So let's substitute our limits. And then now with that b in place, we can see that what's going to happen here is the denominator, e to the b, is going to grow without bound, and the numerator is going to stay the same. So this entire thing is going to go to 0. So my integral from 1 to infinity of 1 over e to the t is going to converge to 1 over e. Therefore, the integral that I started off with, 1 to infinity of e to the negative t over root t dt, is going to converge by comparison. Again, a larger function converged, so the smaller function is also going to converge. And that's going to do it for, 18 through 20. We'll see you next time here, and we should be finishing up here with the Chapter 9 practice test. See you on the next video.